Quantum computing is a full stack, from hardware up to the programming interface. Find out how you can modify just one layer of this stack to dramatically improve the performance of your programs in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the VP of Quantum Software at Infleqtion. I've had the pleasure of not only having him on the show before, but of working with him on events, customer workshops, and some more technical projects you might hear about in the future. Thrilled to welcome back the first three-peat of the post-quantum world, Pranav Gokhale.
Hey, Konstantinos. Thanks for having me as a three-peat. Really appreciate that.
Yes. Always terrific to have you on. And you first came on as co-founder of Superstaq. Maybe you could just give listeners either a refresher or, depending who they are, a quick intro to your background and the software focus of Superstaq.
Yeah, sure. So this was a spin out of research that I did with Professor Fred Chung, my PhD advisor at UChicago. And we were looking at building a quantum stack that was very cross-layer in the sense that we would take applications and tailor them for execution on very specific hardware rather than building a lot of abstraction barriers in between. And the core insight here is that abstraction barriers incur a lot of inefficiency. So the software that we've been developing is about removing those inefficiencies, getting practical results sooner than otherwise possible. And so we were acquired by Called Quanta, now named Infleqtion, a year and a half ago, and now I lead the quantum software efforts at Infleqtion.
Yeah, and listeners might recall that when you were on last time, we were talking about benchmarking quantum computers using software. And the software behind the software was an earlier version of what we're going to be talking about today. So maybe you want to talk a little bit about the evolution of Superstaq?
Yeah, absolutely. So last month, we were really excited to launch what is called the open beta of Superstaq. And this is our flagship quantum software product. It's a platform that we've been developing for about 2 years now. And 2 years ago, we launched it in a very closed alpha. And that was to solicit feedback from users, to figure out the roadmap for what we wanted to build and how we wanted to build it. And over that 2-year period, we got a lot of valuable comments, reactions, usage from a variety of users. So it included universities like Northwestern University, University of Chicago, included companies like Morningstar Financial, and it included national labs such as Berkeley Lab, Sandia Lab, and Argonne Lab. And so many of those users ended up becoming very loyal customers who would use our platform for optimizing their stack. And I guess I haven't really yet touched on what Superstaq is, so I can give a quick précis of that. It's a optimizing platform for running quantum programs on current quantum hardware. And really, it comes back to this insight that if we want to get more mileage out of today's quantum computers, we need to have a very, very efficient compiler that can take applications and put them on the hardware as efficiently as possible. And in some sense, it's kind of like more of the 1960s of classical computing, where programmers like Grace Hopper were actually stepping into the mainframe and doing debugging, removing moths that had flown in, things like that. So, of course, the end user of our stack is not necessarily having to suffer the pain of working with the device physics of a quantum system, but we automate that process and do it in such a way that the end user can get the benefit of this automated compiler flow. So in a nutshell, that's what we've been developing, and now we've made it open to the whole world to use. And in fact, Konstantinos and I got the chance to kind of run a live demo prior to this conversation, which was a lot of fun.
Yeah, that was pretty eye-opening. And it's sort of going to direct my questioning a little bit so users can kind of like be right there with us, I guess. So now this is available to end users, which is exciting because of what can unlock with these performance boosts. So maybe if you could tell our listeners at like a high level how you access this tool and what those initial benefits could be, just so they can get a sense of what it's like to use it. It's right now they're visualizing any number of things, I imagine. So what's it like to even just use it?
Yeah. So the basic step is there's a website called superstaq.infleqtion.com where you can just 1 click, 2 clicks, sign up through Google or email address. And when you sign up, what you're really getting is a password and API key. And from there, anyone who's familiar with writing a quantum program, whether it's with Qiskit or with Cirq or Chasm, can pretty directly plug into Superstaq. For instance, a lot of our users are very familiar with Qiskit, which is a library that we love for running quantum programs. And Qiskit has all these abstractions, things like providers, which give you access to hardware and run jobs. And so we have essentially a Superstaq provider where instead of submitting to the ordinary provider, you submit to the Superstaq provider. The syntax, the usage is pretty much identical, but the big difference is performance. And so when you run, even with the highest level of optimization, a program through Qiskit, oftentimes once you get past a couple of qubits, maybe 5 or 6, you start getting really noise-hampered results. And that makes it kind of challenging to use a quantum computer for anything remotely resembling business-relevant use cases. And so if you take the same programs and just run them through Superstaq, just direct the traffic through there, we do a lot of advanced optimization of the programs and then submit that to the quantum computer. The results that you get back end up being orders of magnitude better, to the point where I almost want people to not take my word for it. I really, really don't want people to take my word for it. It's worth trying out. It's like 5 button clicks to see it live.
Yeah, and when we did that demo together, it was so easy to see, because for listeners to understand, when you run quantum computers, you have to run them a lot of times, and then you have to look and see what answers you got, and then you have to decide if any of them are significant enough to prove that they're the right answer, to rule out all the bad ones. You run it 4,000 times, and sometimes the right answer is only in a handful of times more in one case, so it gets tricky. You can have like 500 correct answers, and then the rest are 4 something in the wrong one. So it's hard to find the right answer. But when we did the Superstaq live, it was so obvious, right? It was like almost every single run was the correct answer, and it was a huge difference. So it sounds like hyperbole, but it isn't. Like if you look at the before and after bar graphs, it's quite impressive. That's why I'm pretty excited that this is available to people.
Yeah, and maybe I can even touch on why it delivers such maybe surprisingly good results.
Yeah, absolutely.
Preempting a potential question. So there are a lot of great tools out there, including Qiskit, including Cirq, including PyTicket, which are really good for what I'd call traditional objectives that just obviously make sense. So for instance, if you have 2 gates in a row that cancel each other out, it's better to remove those because you save some time and save some error accumulation. If it's like having 2 NOT gates in a row, you get rid of those. And so that's the base layer of what previous technologies have done and where we build on top of, and in fact, incorporate a lot of those open source technologies to our platform. But as we were building this, we found that there are a lot of things that are very counterintuitive about running programs that are not supported by open source software packages. And they're all things that have to do with maybe surprising aspects of quantum computing hardware. So one example is I kind of have to retract what I just said, which is sometimes you see 2 X gates, 2 NOT gates, and you would think to remove them. That's what normally Qiskit or Cirq, et cetera, would do. But in fact, we find that oftentimes leaving them in there is better for performance. And this is a technique called dynamical decoupling. It's a very physics-aware technique where one has to see that on very specific hardware, if you apply extra gates, it actually kind of protects the qubits from noise. What it does effectively is it causes noise to operate in counterclockwise at one time point and clockwise the other time point, and therefore it cancels out. So it's this collection of techniques that we've developed that are surprising and counterintuitive that end up having the biggest gains in performance. Another example is crosstalk. So much like being at a dinner party and trying to have a conversation with your neighbor, but then there's a loud neighbor next door, there's techniques that you can do in a quantum system to mitigate this kind of noise as well. And it's not really noise that makes sense to a traditional compiler because there's no such thing as crosstalk, at least practically speaking, for non-quantum computing. But for quantum computing, there is, and you can actually cancel out that crosstalk with the right software. So in a nutshell, that's what we've been doing on the technology and R&D development side that we finally put out into this product.
Yeah, and on the show in the past, we've talked about things that can be done before we get to the error correction days. And one of the techniques is, of course, having a knowledge of the device and what you can do to prevent errors from getting worse along the way. And it sounds like you're accomplishing that right here, which brings me to the next question. Like, which devices are you aware of then with this tool? Like, which devices can you do these things for?
Good question. So several of them. I would highlight a few. So on IBM, we've done really a couple of years of focused development on their system. Another one is the bracket devices through Amazon Web Services. So for instance, on Rigetti, we were able to use this dynamical decoupling technique to quadruple the lifetime of a qubit. And then one of my favorite end users is the DOE National Test Beds. So these are quantum computers at Sandia National Lab, that's a trap-down computer, and the Berkeley test bed at Advanced Quantum Test Bed at Berkeley, that's superconducting. So we also have very sophisticated compilers for their devices that one of the cool things in those platforms is they allow very low-level access where researchers and application developers can kind of almost touch the guts of the quantum computer, and our stack optimizes to those internal mechanics of the machines. So there's a bunch out there. The ones that I mentioned are ones where we've done really last mile optimization that ends up raising performance quite a bit.
A good one to start with is probably IBM, just because people are more familiar, I guess, with Qiskit, and you've done so much on those machines. And it'll be interesting. So do you expect that this type of approach will scale with other technologies going forward? Like if so maybe like the brand new IonQ or something, do you think you'll be able to find gains in all those types of systems?
Yeah, pretty much any gate-based quantum computer is going to have these same device physics properties that our stack is now configured to just be able to read in the underlying device physics and optimize for that. Of course, there are other technologies too out there that are very exciting, quantum annealing, continuous variable photonic quantum computing. We don't really have a compiler for them. We have some thoughts on applications, but that's not the focus of Superstaq.
Yeah, terrific. So we talked a little bit about the demo and the performance numbers. Can you categorize, let's say, a typical boost with IBM? It seems to be, it's really high. Can you give a good example of what that range is for some basic approaches?
Sure, yeah. Maybe I'll start really small, and it'll sound trivial, but I'll explain why it ends up building up quite a bit. So we have the record right now for the best swap gate, that is just exchanging the positions of two qubits on IBM hardware. And that's essentially using these techniques. We've developed a swap gate that's something like 17% faster and 15% less error than the otherwise best swap gate that's used. So that sounds really small, right? But the thing to keep in mind is that this is a multiplicatively compounding effect, where if you have 10 swap gates, then you've got this advantage occurring 10 times over. And in practice, for superconducting systems, which have sparse connections, you need to do a large amount of swaps. In fact, swaps are overwhelmingly the only thing that you really do, more than 50% of operations that you do. So what this technology builds up to, along with these dynamical decoupling sequences that I mentioned earlier, in applications, you see routinely 10 to 100x advantages, and it scales with the size of the problem. So if you run a 3-qubit circuit, Superstaq's not going to deliver any game-changing results. But I think when we did the demo, for instance, we were looking at something like quantum phase estimation, which is a benchmark and a really building block of a number of quantum algorithms. And there at the 7 or 8 qubit scale, we were starting to see huge differences where with previous technologies like Qiskit optimization 3, you really wash out any signal. It's just noise. And with Superstaq, you get more than a 10x advantage in a measure called KL divergence, which is kind of how close am I to the correct probability distribution. So again, this continues to scale up. When you get to the 100 and qubit regime beyond, we expect to see continuing compounding exponentially of this effect. And therefore, it's hard to really assess what the number of the gain is, because on small programs, you get 5, 10x advantages. On big programs, you can get million x advantages. We just like to think of it as more broadly bringing the future of quantum computing sooner. And I think that's powerful because and I know Konstantinos and I, and maybe I'll turn a question over to you, is what we've realized is there's a lot of demand for things that work right now. And there's a lot of hope for quantum-inspired technologies that I'm really excited about your work on. And the reason that we are doing quantum-inspired today, of course, is it runs today, but we're all going to be happy as an industry as a whole if quantum can actually solve real problems next year or the year after. And so we just want to make that happen sooner.
Mm-hmm. Yeah, definitely. Like you said, with quantum inspired, that's what we're trying to do now. But how amazing if we find just that right use case that seemed like it was teetering on the edge, and now all of a sudden, nope, it's viable today. Especially if you can go into the thousands or higher X performance boosts, because some of them are like eerily close at times for just something that you can work with. I want to highlight that this might be a way that we just shorten that timeline to that first use case that's not a toy problem, because that term is thrown around a lot and it's almost annoying, right? It's almost as annoying as stepping on a Lego, like hearing toy problem all the time. I think that we're on the right track here. So it's pretty exciting stuff. So when you get in there, though, if you're kind of new to it and you're not sure what to do, there are a few. I think there's like 3 sample applications that you can dive right into. Did you want to talk about those to give a sense of like what's already sort of been hammered out as things people could just get running with right away?
Yeah, sure. So one of the big pushes for this launch was having excellent documentation, which I have to say is something that engineers often, including myself, forget about the value of until we see users starting to get started. And it's just something that makes a big difference. And during the alpha period, I'd say our documentation was a bit lackluster. Now we've gotten design help. We've gotten a lot of internal team reviews on what sort of documentation we want. Our product manager, Stephanie, has done a really great job of curating like a collection of tutorials. So yes, there are tutorials that we have that are open source, and that includes running things like the Bernstein-Vazirani algorithm on hardware to get better results. It includes things like compiling to hardware that has unusual or non-traditional gate sets. So it's not so much unlike in classical computing. There's always been this RISC versus CISC trade-off. Is your instruction set complex, which is CISC, or is it small and reduced, that's RISC? And so we can kind of, in our compiler, enable talking to a large number of different hardware platforms that have very diverging gate sets all at once. And some of this documentation goes over that as well. One of the other things is there's the tutorial notebooks, but especially now with integrations like Copilot, it also matters to have really great function documentations. That is every class and every method well characterized and well documented. So that was not necessarily in the tutorial, but when you get started to use all this stuff, can a user go into some code that's not been explicitly covered in a tutorial, but actually run it and understand what's going on? And I think we're hitting the mark there now that we're in open beta. Maybe I can touch on to one of the cool things that one of our early users did, which really blew us away. So this is one of our customers at Argonne National Lab got some of the early licenses to Superstaq. And there's a gate called the Toffoli gate in quantum computing, which Konstantinos will know, but it's basically for the viewer an AND gate. That is, it takes 2 inputs and reports back if both of them are true. But it does this in a reversible quantum mechanical manner. So it also copies the inputs over. And this is something that's really hard to decompose, especially if you have a limited connectivity device. There's some textbook decompositions, and they kind of bottom out at performance that's just not that impressive. And so our user at Argonne devised a better decomposition of this really fundamental gate using Superstaq and using lower level access to the primitives that are available on IBM. So nowadays, this is built in a format that any user can run without really thinking through the device physics of what is IBM's superconducting qubit doing. But this was enabled by this researcher who went and used Superstaq to draw pulse schedules that are very analog and very unconventional. But building up that, he produced this really awesome result and benchmarked it with something called quantum process tomography, which is one of the gold standards for, is this gate doing better than the one I had before? And saw a really substantial improvement. So that is maybe the most advanced tutorial, back to your question, that we have out there, because it's actually an academic paper that was just published on September 28th in, I think, IEEE or ACM Transactions in Quantum. So there's a whole spectrum. There's like the easy stuff to get started on. And then there's researchers like Argonne, Berkeley Lab, Sandia Lab, who are using the software to actually push the frontiers of what their quantum systems can do.
Yeah, so I was going to ask, there's a mechanism for people who start to play around with this and get good results to feed back in to the community, sort of?
There is, and we maintain a Slack channel, a Slack workspace, where we have had 24/7 conversations with some of our early users who are getting their feet wet. And honestly, their input is amazing for us too. That's why we are still calling this a beta stage, because the user input is going to feed back into our product at a time scale of like hours and minutes, not months and quarters.
So some of this, I'm assuming, feeds back in also as like bugs or just features that are more built in rather than things you have to recreate with some kind of tutorial, right? Like just ways that the software will behave better behind the scenes without even thinking about it.
Yeah, that's right. And so behind the scenes, we're running this project board that keeps track of any sort of performance regressions or issues noticed by users, and have this kind of agile methodology for reacting to them.
And do you know of any applications that are almost ready to be released that maybe even want to talk about now to get people interested in them, or are there things that they can be expecting soon that aren't there now?
Good question. So one of the ones that we do have a tutorial notebook out right now, but I'll maybe use this opportunity to kind of talk a little bit more about it and get people interested. We put out a paper last year called Supercheck, and Supercheck is essentially a quantum protocol that we developed for fingerprinting data. So let's say Konstantinos and I both have season 6 of Game of Thrones on Blu-ray or whatever. And we just want to make sure we have the same data. Perhaps I'm worried that mine got corrupted when I walked home with it in the rain or something like that. So one method is I could send that entire Blu-ray file to Konstantinos over the internet, but actually that's a huge amount of data. It will take minutes, if not hours, to transmit, to the point where it's almost faster to mail it to Konstantinos. And in fact, this is what Amazon Web Services does for very large data sets that need to be transferred. But Supercheck is this quantum protocol that's built into Superstaq, where a user can check if two classical files are equal by effectively kind of compressing the files into a very small number of qubits. So if you have a 100 gigabyte file, you can compress it into a few dozen qubits. And this is something that's now integrated with our stack. I'm looking forward to some potential user trying it out on real hardware. We've done some initial tests, but it can be done on really any hardware platform. And I think that would be one of the new frontiers that I anticipate developing more. I'll give a bit of a spoiler alert. We're going to have a version 2 of our paper coming out quite soon that shows exponential advantages over the best possible protocols while maintaining this incrementality property. And maybe that's too into the details, but it's really exciting and has caught a lot of attention, including we just demoed it to the Australian Army in Perth. One of our team members, Kate Smith, went over there to show it. So that's very front and center on what users are able to do today that is at the cutting edge. And then looking a couple of months down the road, I expect we'll see some really nice results on some quantum machine learning algorithms Something called the swap test is pretty cool. That's where you can check if two quantum state vectors are similar or not and quantify how similar they are. And that's a quantum circuit that one of our users has been benchmarking and has some pretty exciting results for. So I expect to see community-driven tutorials as well. Again, the tutorials are open source with the documentation. So we think there will be a lot of users who jump on.
And of course, this is for if you're looking for inspiration, new things to try. But at the end of the day, there might be code that you're running right now that you just want to see if you can make it run 10 times better or more, right? And that's like super eye-opening if anyone gets that to work.
Yes. And I'll also put a plugin here, if it's okay, for work that we've been chatting with you and Protiviti about, which is on some financial applications for, let's say, credit card fraud detection. So we've been partnering and thinking about how we can help out customers who are looking for quantum models there. And I think that would be another exciting space where, let's say, some credit card company is going to have, or financial firm might be able to come up with the basics of an Oracle or quantum circuit for running proof of concept. But if they're in a position where the first iteration is just going to get washed out by noise, I'd love it if they can just do like 2 lines of code, import Superstaq, run through Superstaq, and get great results thereafter. So that's kind of where I'm hoping some of this will play out.
Yeah, especially if there are some hard edge cases or something that Classical's struggling with. Like the other work we did, we were able to show some pretty big boosts just in using digital annealer, for example, in some cases with the F1 scores and things. So yeah, that's definitely one way to go. So I really encourage listeners who are just working on whatever right now to consider that this might be a game changer, and to definitely get involved. And of course, in the show notes, we're going to have a link to the docs, which from there you could just click and actually try out the software. So is there anything they need to know about trying out the software? Is there what considerations do they have to have in mind for getting an account?
It's pretty seamless. So it's the front end, the client is open source. You can check it out with the Apache license. If you're wondering what is the business model here, we have limited usage for the free trials. And of course, that's because, we protect some of our proprietary techniques, which are patented in the server. And so what the signup really enables users to do is get free credit to access the server. No time limit, just if someone is going to run 100,000 calls to our server, we want to make sure we're prepared to support that. So that's really the business model around scenes here. But it's pretty seamless to get started. Run several circuits on IBM, several circuits on the Amazon Web Services backends, several circuits on another number of other devices that we support. And the fact that the front is open source, I think, helps make it pretty transparent as to what we're doing. The other thing that we made a really concerted effort to do is, similarly in the spirit of transparency, have as much visibility for the user as possible in terms of what is going on behind the scenes. And again, many, many users, if not the vast majority, won't really care about what are the pulses operating this. But for the users, especially from a research community who want to know what is going on behind the scenes, we make sure that we show what is happening when you press run, what are the pulses that are running, what is gate representation of each pulse, what are the error parameters. We make measurement error mitigation optional. This is a technique that I think is really powerful, but it also can sometimes obfuscate results. So rest assured for any interested listener that you'll have a lot of knobs to play with. There will be defaults that are easy to get started with, but you can often turn off the defaults if you want more and more visibility into the process that's underlying.
Yeah, and if you're not super technical and you're interested in having someone help you with a quantum project, we would be able to show you, I guess, before and after, like how much better a use case or whatever will run. So it'll be exciting to see what we come up with going forward on this one. Yeah, thanks so much for making this available to anyone who wants to experiment with it, and for coming on here to let the world know about this.
Absolutely. And maybe one question I have for you, if that's okay, is having seeing the whole quantum landscape, what are you excited about for, let's say, quantum software or hardware that I'll take as feedback as well to internalize to future iterations of Superstaq, and perhaps ones that you might be on your mind right now that you want your listeners to hear about?
Yeah. I definitely want to see the ability to boost performance greatly. Because we've been so hampered still. Like it just feels like we're kind of stuck with machines just ever so slightly getting better. So I'm excited right now to see how an approach like this would just be affecting everything across the board. All the stuff that we've been doing for the past couple of years, just like give it a fresh look, a fresh set of eyes. So I'm kind of excited to try this against almost everything, to be honest with you, for that approach. And also, is there anything like this that can be done for maybe the world of annealing? I don't know. Is there a way to like shift over?
That's a really good question. We have some thoughts in that direction. Nothing product ready, but I guess one of the things I'll observe is there isn't necessarily as much of a distinction between gate model and annealing as there needs to be, quantum annealing, in the sense that quantum annealing is really an analog process. And what we talk about as gates is really under the hood an analog process. And so one of our actually researchers at a national lab who spoke with us recently is interested in seeing if they can use Superstaq to perform quantum annealing on traditionally gate-based devices. So imagine if you could use IBM's 1,000-qubit machine and interspersed with gates, but in between you've got an annealing protocol, so you get potentially the best of both worlds. That would be really exciting. We don't have that yet today, but could be cool to see.
Yeah, or can this be applied to like the whole analog mode of machines like like Quera or something like that, right?
Definitely.
So other stuff to work on, I suppose. We'll probably have you back on when you succeed with that.
Number 4.
Yeah, or might have you back on if we succeed at a few other things we're working on right now.
That's true.
Once again, my friend, thanks for coming on, and good luck with this new launch.
All right. As well, as always, appreciate your time, and thanks for having me on.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Superstaq is an optimizing platform for running programs on current quantum hardware. Before sending your code to, say, an IBM system, you pass it through Superstaq, where it will be optimized to run on that hardware and will return up to orders of magnitude better performance. The software works with other hardware too, such as systems on Braquette, Rigetti, and even DOE national testbeds. How does it work? Some of the techniques used have been around for a while, such as removing redundant gates. However, Superstaq goes much further, including understanding the device physics involved in specific systems. As a result, the software can even handle some of the noise that enters an execution, especially as more qubits are used in a circuit. Superstaq can use dynamic decoupling to extend coherence times, where it adds extra gates to protect qubits from noise. Noise accumulates in one direction for half an operation and the other direction for the other half, for example, canceling out. The software also makes improvements to swap gates, which are the most common operation in a circuit. Adding up lots of faster swap gates and reducing noise using dynamic decoupling can yield stunning results. Superstaq routinely improves performance by 10 to 100x. But in some cases, with very large programs, Pranav says Superstaq should be able to improve performance in the million-x range. These are the kinds of boosts that could make NISQ computing provide real types of advantage today, before we get fully error-corrected qubits. It will be exciting to see the results over the next year or two of experimenting with this. And lots of companies are already experimenting with this. If you'd like to join in, check out the link in the show notes to read more about Superstaq and sign up for access. There are tutorials and sample code to get you started. That does it for this episode. Thanks to Pranav Gokhale for joining to discuss Superstaq and Infleqtion. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to find me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.